In this video, we are going to talk about Gregory-Newton backward interpolation formula, or it's also called Newton's polynomial in backward difference operator form. So we will start with only two data points, x0, y0, x1, y1, and this is an equally spaced data. Just know that for Gregory-Newton backward interpolation and Gregory-Newton forward interpolation, that is Newton's polynomial in forward difference operator form and Newton's polynomial in backward difference operator form, we shall use equally spaced data. And for divided difference operator, we shall use not equally spaced data. So we are going to write Newton's polynomial in backward difference operator form. So here the Newton's polynomial will be slightly different as compared to what we wrote for Newton's polynomial in forward difference operator form and Newton's polynomial in divided difference operator form. So you know that your data is equally spaced, and the next thing that you have to do is whatever is your last x, here it is x1, you call it xn. And the value behind x1, which is x0, you then call it xn minus 1. So the corresponding y values will be y1 will be yn and y0 will be yn minus 1. So we are calling x1 as xn, last x, which is here x1, we are going to call it xn, and y1 as yn. And the value behind xn is xn minus 1. So x0 will be xn minus 1 and y0 is yn minus 1. You only do this when you are writing backward interpolation formula. So the Newton's polynomial will be of degree 1 because for 2 points the maximum degree of the polynomial is 1. So we write p1 of x equal to, we write a0, no linear factor along with a0. Since it is p1, so we stop at a1 and 1 degree linear factor. Now remember, when we are writing Newton's polynomial for forward difference operator and for divided difference operator, our polynomial was p1 of x equal to a0 plus a1 x minus starting x value, which was x0. But here, since we are starting with the bottom of the data, that's why we have called x1 as xn. So in Newton's polynomial for backward difference operator, we shall write a0 plus a1 x minus the last x. Here the last x is x1, but we have named it as xn. So that's the Newton's polynomial of degree 1 for backward difference operator. Since we have two unknowns here, which are a0 and a1, to find these unknowns, we will use two conditions. What are those two conditions? If in this 1 degree polynomial, in the place of x, I plug xn, I must get yn. If in the place of x in the polynomial p1x, I plug xn minus 1, I must get yn minus 1. It's like the verifying conditions on these 2 points. So let's call this Newton's polynomial of degree 1 as 1. To find the first unknown, which is a0, I will compare the equation 1, p1 of x equal to a0 plus a1 x minus xn with the first condition p1 of xn is equal to yn. Let's compare left hand sides. p1 is same as p1 and x is same as xn. So put this x equal to xn in the polynomial in equation 1. See what we get. p1 of xn, because in the place of x we are putting xn, a0 constant as it is, a1 constant as it is. In the place of x we have xn minus xn. And we can see that from this condition p1 of xn is actually equal to yn. So the left side we are keeping yn equal to a naught. So what we are seeing is the value of the first unknown, which is a naught, is yn. Remember when we found a naught and a1 in Newton's polynomial for forward difference operator and Newton's polynomial for backward difference operator, we had a naught as y naught, the starting y. But here we have a naught as the last y, which is actually y1, but here we have named it as yn. And a1 was y1 minus y naught over x1 minus x naught, both for Newton's polynomial for forward difference operator and divided difference operator. And we are going to see what we get for a1 for the polynomial in backward difference operator form. So to find a1, we compare this polynomial 1 with the second condition. So we compare p1 of x equal to a naught plus a1 x minus xn with the second condition, which is p1 of xn minus 1 equal to yn minus 1. First comparing the left side with the left side. P1 is same as p1 and x is same as xn minus 1. Plug this x equal to xn minus 1 in the polynomial. So we get p1 of, in the place of x we have xn minus 1. A naught, we found a naught as yn plus a1, which we yet have to find. In the place of x we are putting xn minus 1 minus xn. We know that p1 of xn minus 1 is yn minus 1 equal to yn plus a1 xn minus 1 minus xn. We will extract from here a1, which is yn minus 1 minus yn equal to a1 xn minus 1 minus xn. So a1 can be written as yn minus 1 minus yn divided by xn minus 1 minus xn, or from both numerator and denominator we can take minus common and we have yn minus 1 divided by xn minus xn minus 1. Now we know that our data here is equally spaced, and for an equally spaced data we know that x1 could be written as x0 plus h. We have seen this before. x2 can be written as x0 plus 2h, and so on. xn can be written as x0 plus nh. The same way xn minus 1 can be written as x0 plus n minus 1h. Let's put the value of xn and xn minus 1 here in a1. a1 is yn minus yn minus 1 divided by xn is x0 plus nh, and xn minus 1 is x0 plus n minus 1 h, and we will put the parenthesis outside. a1. Now recall the definition of the backward difference operator. yn minus 1 can be written as backward yn. Look at the definition of the backward difference operator. Backward difference operator on y3 can be written as just y3. It stays at the same number minus one value behind y3, which is y2. So same way backward yn will be, it stays at yn and one value behind yn, which is yn minus 1. So here we have written backward yn divided by, let's simplify the denominator, x0 plus nh minus x naught minus n minus 1h, which can be further simplified. A1 is backward yn over nh minus nh plus h. So we have a1 as in backward yn over h. So we have both of the coefficients now available. A naught was last y, which was yn, and a1 is backward yn over h. So the Newton's polynomial for the backward difference operator was a naught plus a1 x minus the last x. Now we plug in the values of a in the backward difference operator form, which is yn plus a1 is backward yn over h x minus xn. So this is Newton's polynomial in backward difference operator form. It is of degree 1 and it is also called Gregory-Newton backward interpolation formula, and it is also of degree 1. Now let's make the comparison with the forward difference operator polynomial coefficients. If you can recall, in the forward difference Newton's polynomial or Gregory-Newton forward interpolation formula, a naught was y naught, a1 was forward y naught over h, a2 was forward square y naught over h square 2 factorial. This was for forward interpolation. But now we have seen that a naught was yn. See the comparison. In forward interpolation, a naught is the starting y, and in backward interpolation, a naught is the last y, which we are denoting as yn. And we got a1 as backward last y over h. And here we have forward y naught over h. The same way, following this pattern, if we have to write a2 for backward polynomial, we will write backward square last y, which is yn, divided by h square 2 factorial. Just like for forward interpolation, we can write a3 as forward operator cube because it's a3. Acting on the starting y, it's always the starting y, divided by h cube 3 factorial. But if we have to write a3 for backward difference operator, we will write backward cube because it's a3 acting on the last y. Last y is denoted as yn, divided by h cube 3 factorial. So let's write backward difference Newton's polynomial for 3 data points: x0, y0, x1, y1, x2, y2. And these data points are equally spaced. So what you do for backward difference operator polynomial, you write whatever is your last x as xn. Here x2 will be called xn, and then y2 will be yn. One value behind xn, yn will be xn minus 1, yn minus 1. Another value behind xn minus 1, yn minus 1 will be xn minus 2, yn minus 2. So here we have 3 data points. So maximum degree of the polynomial will be 2, p2 of x, and we are writing Newton's polynomial for backward difference operator. First we just write Newton's polynomial a naught a1 x minus, since this is a backward Newton polynomial, so instead of writing the starting x, we will write the last x, which is xn. So it's like we are going from the bottom of the data to top, plus it's p2, you stop at a2, two factors. One is the previous one, which is x minus xn. So you have covered the last x. Now the x behind it, which is xn minus 1. So we write x minus xn minus 1. This is just the Newton's polynomial for backward interpolation. But now we are going to change this Newton's polynomial into backward difference operator form. For that, we just have to write the values of a naught, a1, a2. So a naught in backward difference operator form now we know as just last y, which is yn. a1 is backward yn over h, and a2 is backward square yn over h square 2 factorial. So let's put these values a0, a1, a2 in the Newton's polynomial, and then this polynomial will become Newton's polynomial in backward difference operator form, or Gregory-Newton backward interpolation formula. So a0 is yn, a1 is backward yn over h x minus xn, plus a2 is backward square yn over h square 2 factorial x minus xn into x minus xn minus 1. So it's 2-degree polynomial, 2-degree Newton's polynomial in backward difference operator form. So in the next video, we will construct from the given data set backward difference table, forward difference table, and divided difference table.